Hello, ladies and gentlemen. Time for a little overview for Unit 3, Lesson 3 of the Raise Set Go part. And get some practice in here. So in the first section of the Raise section, it gives you a couple of functions, and you need to find the point at which these two functions meet, the two lines meet. And so it gives you a table, and you fill them in and all that stuff. So we're going to use number 2 as our example here. I'm going to use this one because the tables are blank. So there's nothing in the x's column. That means you can pick whatever x's you want. I don't know, I like starting at 0 and counting up from there. And the thing is, sometimes the points you pick aren't going to be where the intersections are, so you may have to pick additional points. We'll see if this one works. So we're going to just plug in 0 here. 0 plus 2 equals 2. So put that there. And then you can plug in 1. Yeah, 1 plus 2 equals 3. So we got 3. And let's just plug these in. 2 plus 2 equals 4. And hopefully you realize that this is linear. This is the y-intercept that goes there. And then my slope here in front is 1. That lets me know it's just adding 1 each time. So I know it's going to go 2, 3, 4, 5, and 6, like that. All right, well, let's go to the other one here. Let's use the same numbers here and see if any of the rows match up. So we're going to plug in 0. 2 times 0 is 0. And then my slope here lets me know it's adding 2 each time. So I'm going to do 2, 4, 6, 8, like that. Let me draw the 8 better. So I got my tables filled in. And you need to check the rows and see if any of them match. So we got 0, 2, 0, 0, nope. 1, 3, 1, 2, nope. 2, 4, 2, 4. Hey, look, they both had the point 2, 4. And so that's going to be the point where these two lines meet up. And we're going to write that down. Hooray. So that's what's going on in that section. You just have to fill in the tables and see where the points are, where they meet up. So there's our first section. The next section, the set section, starts with some statements. You have to figure out if they're true or false. And if it's false, explain why. I'm just going to look at a couple of these. Question 7, exponential functions have a domain that includes all real numbers. As a reminder, the exponential ones are functions that have some start number and is times by something each time, which often makes a shape looking like this. Or it might be coming down like this. Either are exponential. In any case, these functions do go left and right forever, so you can pick any x value you want and plug it in, and it'll be fine. You'll get a y value that comes out of it. And so this one is going to be true. The domain is all real numbers. Any number you could possibly think of, you can plug in. At least any real number you can plug in. And then let's go to question 8. Geometric sequences have a domain that includes all integers. So the all integers are things like -3, -2, -1, 0, 1, 2, 3. And it just keeps going in either direction. Well, this... just kind of by the strict definition of geometric sequences, is going to be false. And that's because typically when we have sequences, we don't use the negative numbers. We just use the positive ones, right? If you have f of n equals f of n minus 1 stuff, right? All that things with sequences. This n was the term number. And so you'd start with the first term number, and then the second term number, and third term number, etc. You don't go to the negatives. So we're going to put false. We're going to say the domain is the natural numbers. Okay, there we go. So, sometimes it's true, sometimes it's false. If it's false, give an explanation why. Let's look at another one. We've been working on this for quite a bit now. There's a function. You need to write down these properties for it. This is about position relative to the surface of water. Last few minutes of a person's snorkeling trip. So they went down underwater, kind of go up and down, and then they come out of the water. So when you write down the domain's how far left and right this function goes. Well, it does have a distinct start point here, which that x value is 0. And then it stops over here, which is about halfway between 13 and 14. So we can go from 0 to 13.5. The range, on the other hand, range is how far down it goes versus how high up. The highest it goes up here is 3, and the lowest it goes is here, which is like, I don't know, negative 3.8-ish. So I'm going to do that, negative 3.8-ish, and then all the way up to 3. And actually, I need to do square brackets on these. Sorry, I messed that up a little bit. Because it does actually hit those numbers as the end of the interval. The maximum, that's going to be over here, which we said was about 13.5, and the height's 3. The minimum is going to be at this point here, which is about 1, and then negative 3.8. The intercepts, it does have an x-intercept here. It has a y-intercept over here. So we got x1 at, let's see, it's like 12.5-ish, 0. And then we have a y-intercept at 0, negative 3.5-ish, right, down about 3.5. The intervals of increasing. Well, we have a lot of sections here. It does start by going down, and then this is all increasing until here. So we've got this little window. And then it decreases, and then it increases again from here all the way to the end. So to the right of 6, and then in this little window. So our first interval goes from 1 to 4. And then we're going to put a U. The next one goes from 6 to, well, not infinity. It doesn't keep going. It does stop at about 13.5. So there we go. We do have 2 intervals where it's decreasing. So it's decreasing right here. So that goes between 0 and 1. And then it decreases from 4 to 6. So 0 to 1. Put a U there. And then 4 to 6. All that stuff. And the last one, is it discrete, continuous, or discontinuous? It is continuous. It's all connected. There's no breaks here. So that means it's going to be continuous. So yeah, that's what's going on this section. You have different functions. There's a recursive rule from sequences. There's another graph here that's discontinuous. It's got spots for broken. And then in the Go section, you need to write the recursive and explicit functions for the things. So we're going to use 15 as an example. Just remember how these functions work. It looks like my n's are increasing by 1, so it's just adding 1 each time. That's great. And then my f of n's here, it looks like it is all times by 2. That means this is geometric. And our growth factor, or common ratio, is 2. So when I write my explicit, I'm going to do f of n equals, the part that makes this a little bit different is it doesn't start at 0, it doesn't even start at 1, it starts at 2 for n. I am going to put that starting number of 4, and it is times in by 2. But up here, I'm not going to use n or n minus 1. I'm actually going to use n minus 2, and that's because it starts at 2. And so I'm going to put that up there. If this started at 7, then we would make this 7. Whatever number you're starting at is going to be n minus that. And that's because when you plug in a 2, this becomes 0, and that cancels that out, and you're just left with the 4. It just doesn't cancel out. It makes it 1. Anyway, time for recursive part. For recursive function, this is where you say where the pattern is. Every number is the previous one. And what do you do with the previous one? We talked about that already. It's times by 2, so I'm going to put times 2. Often if it's multiplying, we'll put the number in front. And when you write a recursive function, you do have to say where it starts. Our first term, or rather the f of 2, is 4. Once again, if this was 7 or something like that, you'd put 7 here. Just whatever number n starts at is what you're going to put there. So there you go. Reminder of how to write out your functions for those remaining ones. And there's your overview for how to do the Unit 3, Lesson 3 Arrays That Go.